Welcome to homework.
Okay, we have a mixture that contains 3 grams of the positive rotating 2-bromobutane, positive polarization, and 2 grams of negative rotation 2-bromobutane. We are told that the specific rotation of positive polarized 2-bromobutane is plus 23 degrees. And so the question then is, what is the rotation of our mixture? Well, recall that what we need to do is figure out what the percent excess of our most abundant polarity component is, right? And so effectively what we do is we say, okay, what's our total grams? 5 grams. Okay, then what percent do we have of the positive rotation? We have 3 grams divided by 5 grams times 100 equals 60% positive rotation. And by process of elimination, or you can calculate it, 2 grams over 5 grams times 100 equals 40% of the negative rotation. And so finally, what we're going to do is subtract the lower percentage from the higher percentage. 60% minus 40% equals 20%. And so what we're saying is that our solution is 20% in excess of the positive rotation. And the way this manifests in terms of the rotation of our mixture is that it will have 20% of the rotation of the pure enantiomer. That is, it will have a rotation of plus 23 degrees times 0.2, or 1/5. And so we get 23 times 0.2 equals 4.6 degrees, and that's positive 4.6 degrees. Okay, so that is question 7. The next question, question 8, asks us to draw the cis and trans geometric structures 1,2, 1,3, and 1,4 isomers of diterpenoylated cyclohexane using chair representations. So here's our chair. So this will be for the cis, and we'll use this for the trans. Let's do 1, 2. All right, so this is cis, and let's do trans. Which of these is less stable? The one with 2 axial groups, which we're told to cross out, then circle the better one. Okay, as we said, this is 1, 2. Let's do 1, 3. Let's draw our chairs. Just a series of parallel lines to draw your chairs. Okay, starting with cis again. Oh, my mistake, cis. All right, same side of the ring. And trans. Okay. And so we have then that our cis has 2 axial, which is going to be higher energy, and our trans has only 1 axial. And finally, 1, 4. Draw our chairs. cis, and trans, 1,4 this time, axial. And cis would be same side of the ring. And now trans, axial, and axial, meaning now this is the higher energy conformer and this is the lower energy conformer. However, recall that you can do a chair flip on any of these structures, right? And that trans will be converted, will stay trans, but axial will be converted to equatorial, and equatorial will be converted to axial. So if we look at any of these examples with two axial substituents, a chair flip of that would provide a structure that has the same designation, trans in this case, but would be two axial equatorial substituents, like so. Right, so now this would be equatorial, and this would be equatorial, such that now this depiction is the lowest energy conformer. Right, this trans depiction is better than either our original cis or trans, and we can do the same thing with our 1,3, right? A chair flip of this particular 1,3 1 becomes equatorial, and 3 also becomes equatorial, right? And a new representation of cis, meaning the lowest energy is now cis. And finally, one last chair flip of this 1,4 trans. Right? We'll place now this as equatorial, and 4 also as equatorial. And 2 equatorial substituents would be the lowest energy possible.